Okay, so we have looked at lots of different different series. And in fact, let me just do, I think I have a quick review here. I thought I had a series. Oh, I know where it is. It is right here. No, it's not. Where is that thing? Series review. Okay. So we're going to talk a little bit just quickly before we go into power series. So we had a sequence is just a list of numbers. A series is the sum of a sequence. We talked about a sequence converging. That meant we just looked at where the numbers were actually going. So we looked at the limit of a sequence. And then we went on to look at the sum of a series. So we have a series A, and if we can sum it and get a number, then the series is convergent. Otherwise, it diverges. So the series we looked at was a geometric series and a telescoping series. And these series, you can actually find the sum. Okay, so if they converge, you can find the sum. I put it in a block. Okay. Then we had the nth term test of divergence. It is the only test that determines divergence. Okay, does not determine convergence. And then all the rest of these tests, which are, and I think I left space for the last two that we did, which was the ratio test and the root test. And so we had all of these tests that we could use to determine if a series converges or diverges. So we had the integral test, we had the p-series test, the direct comparison test, the limit comparison test, the alternating series test, the test for absolute convergence, the test for conditional convergence, the ratio test, and the root test. And so here I put in a block. This test determines convergence, and so the only ones that are missing here are the ratio test and the root test. Okay, so this is the extent of all that the tests that we can possibly utilize to determine convergence of a series. Does anybody have a question? Okay, so on Thursday, we may have a little quiz on this. And I think I'll make that kind of fun. So we'll see what we can do with that. Okay, so let's go back to here and go to module 8. And this is where we are. So module 8 has 3 sections. The first section is called power series and functions. So we want to identify a power series and provide examples of them. We are going to determine the radius of convergence and interval of convergence of a power series and use a power series to represent a function. Okay, so this is what a power series looks like. A power series is of the form. This term is the AN. That whole thing. So the AN is the constant Cn times x minus x naught to the n. And notice that this power series is of that form and it is a function of x. Okay, so it is a power series is a function All right, so notice it has X in here and X naught, it's a constant, and Cn may not, Cn is dependent on N. Okay, so let's write that X naught a constant. In other words, it's a real number. And our value Cn dependent on N. Okay, any questions about that? So please write that down. That is what a power series looks like. And I have examples. Okay, so here's the first example. So this example, my X naught is 0. So here, where I have X minus X naught is 0, so I don't have that term. And then my CNs, which are what goes in front of the X minus X naught, is just 1. Okay, so where I have the summation 0 to infinity of Cn times X minus X naught to the N, that's the summation N equals 0 to infinity. Cn is just 1, and this becomes X minus 0 to the N. And that's just the summation N equals 0 to infinity of X to the N. All right, and if you write it out, the first term is X to the 0. Any number to the 0 is 1. The second term is X to the 1, then we add X squared, then we add X cubed. And this is the first example of a power series. Okay. I think I just missed all of that good stuff on the recording. I don't know why. Okay. Well, at least it's on the notes. I think all that good stuff was missed on the recording. So, okay, wait a minute now. Okay, so let's do a quick review. So for this first series, we had the summation N equal 0 to infinity of X to the N. We said it was a geometric series. We said because A is equal to 1 and R is equal to X, it'll converge if the absolute value of R is less than 1, and it'll converge to 1 minus R. So we got our first series representation of a function. Then we said that it's converged on the interval -1, 1. And if we go back now, we can even say its radius of convergence is 1. So we can go back and say that. Okay, so this next one, we were able to figure out that this series is an alternating series. Where does this series converge? Well, we basically said the factorial screams us to use the ratio test. All right. So we used the ratio test, the absolute value of an plus 1 over an, and took the limit as n approached infinity. We got 0. So we said it always converges. So its radius is infinity, and its interval of convergence is -infinity to infinity. Then this last example, we had -1/2 to the n x minus 3 to the n. And so for this problem, we do have a choice. We have the ratio test or the root test. And so we used the root test, basically because everything was raised to the nth power. So we could use 1 over n. And we were able to show that the absolute value of x minus 3 is less than 2. So that was our radius of convergence. And then we found a preliminary interval of convergence where we weren't including 1 and 5. And then we went and checked and showed to ourselves we could not include 1 and 5. And so that was our interval. Okay, so here I have the same thing. For this problem, we have a choice. We have the ratio test and we have the root test. Okay, I have a preference. My preference would be the root test. Okay. And so for this one, I'm going to use the root test. It's much easier, although the ratio test is not difficult on this one. Okay, so we're using the root test. So a sub n is x to the n divided by n, the square root of n, times 3 to the n. Okay, so that kind of does really say, let's use the root test. Okay, so everything's positive. That's great. So the absolute value of an simply is just going to put the absolute value of x inside here. And then the n, the square root of n, and 3 to the n don't change. Notice, this series starts at 1. Can't start that series at 0. So some series will not start at 0. Okay, any question about this so far? Okay. So rho is the limit as n approaches infinity of the nth root of the absolute value of an. But that's the limit as n approaches infinity. Now we know that the nth root is just to take the absolute value of an to the 1 over n power. All right, so that's the limit as n approaches infinity. So I'm going to take this whole thing, the absolute value of n, divided by n. I'm going to write this nth root as n, the square root as n to the 1/2. And then I'm going to write this as 3 to the n, to the 1 over n. All righty, now that's looking good, looking good. Okay, so rho, the limit as n approaches infinity. Who's going to simplify for me? You guys can do this. Who's going to simplify for me? You take the absolute value of x to the n and then raise that to the 1 over n power. What do you get?
Absolute value of x.
Get the absolute value of x. Okay. I'm going to get n to the 1 over n. Then I'm going to get n to the 1/2 to the 1 over n. I can write that as n to the 1 over n to the 1/2 power. Does everybody see that? So I'm going to write this as n to the 1 over n to the 1/2 power. I'm going to extend my line here. And then I get 3 to the n to the 1 over n, so that just gives me a 3. Okay, so now there's some cool things that we got to remember. All right, so let's just recall a couple things. So the limit as n approaches infinity of n to the 1 over n is equal to what? What is that limit? That was one of the special limits of sequences that we did that I told you you had to remember. The nth root of n is, and the limit is what?
Would that be 1?
It is 1. Thank you, thank you. All right. Okay, so therefore rho looks like the limit. Oh, we're going to get rid of the limit. We're going to evaluate the limit. So when I evaluate the limit, I just get the absolute value of x, and in the denominator, I get 1 times 1 to the 1/2 power, which is 1 times 3. That's it. That's rho. Okay, so now we know the series converges by the root test only when rho is less than 1. All right, so the best the root test can give us is it's convergent when rho is less than 1. So that implies rho, which is the absolute value x over 3, is less than 1. So we get the absolute value of x has to be less than 3. Well, wow, there we go. That is the radius of convergence. Okay, so we got a radius of convergence. It is 3. Okay, then we have a preliminary. So when I do -3 less than x less than 3, this is now my preliminary interval of convergence. Okay, so why is it preliminary? Why is this a preliminary interval of convergence? Why am I not done? Why am I not done?
Because don't we have to find if it works?
Okay, well, we've already showed that the series, so that's a good question, a good statement. We've already shown, though, that we know that it's going to converge whenever rho is less than 1. So I know it's going to converge in this interval. What I don't know is, can I include -3 and 3? Because the root test does not allow me to set rho equal to 1. So I still have to test. So we still have to check, does this series converge at -3 and 3? So we still if this series converges for x equal to -3 and 3. All right, so we still got to do that because we still have to check the ends of the interval. So the ends of the interval here are -3 and 3. So we have to check those. Right now, we know that it works inside of there. Does it work at the end? Okay, so let's check the endpoints. And I think this is actually going to be quite reaffirming for some of the stuff you've already learned. Okay, so let's start with x equal to, doesn't matter. So let's let x equal to -3. We'll start on the bottom end. Nope, I'm gonna start at the top. Start at x equals 3. Okay, so now I gotta go back and remember what the series looks like, and I think I have it. I think I should just be able to do control V. Nope, that's not it. Here's the series. Okay, so here's our series. All right, so when x is equal to 3, this looks like the summation n equals 1 to infinity of 3 to the n divided by n, the square root of n times 3 to the n. And how nice it is that 3 to the n divide out. So this is the sum, n equals 1 to infinity, a 1 in the numerator. And I have n times the square root of n, so that becomes n to the 3/2. Okay, whoa, that looks cool. What kind, I don't know why this won't give me, there we go, I got what I wanted. What kind of series is that?
Wait,
P
wait.
series.
Yes. Who said wait? Come on. Who said wait? I need to make it clear. Somebody said wait.
No.
My fault.
Okay. Everybody good?
Yeah.
Okay, now we already identified this as a P series. Oh my gosh, I'm so proud of you guys. P series, what is P?
Well, 3/2.
Good. So does this series converge or diverge?
Diverges since it's not less than 1.
Okay. P series and rho are the exact opposite of each other. Okay, so the P series converges for P greater than 1. So this converges. Okay, so the first thing is we now can note the series converges when x is equal to 3. All righty, let's check the other endpoint. So let's let x equal to -3. All right. So we get the sum now becomes the sum n equals 1 to infinity. I'm going to get minus, whoop, I'm going to get -3 to the n divided by n, the square root of n, 3 to the n. So the 3 to the n's are going to cancel, but the -1 to the n remains. So now I'm just going to get n to the 3/2. Okay. Now, there are two ways to show this thing converges. One, we can use the alternating series test. That the series converges. Or two, we can look at the sum n equals 1 to infinity of the absolute value of -1 to the n over n to the 3/2. And that is just the sum n equals 1 to infinity of 1 over n to the 3/2, which converges. We already showed that. So hence, this sum, n equals 1 to infinity of -1 to the n over n to the 3/2 converges absolutely. But that just implies that it converges. So now, we can note that the series converges when x is equal to -3. So we have the series converging at x equals 3 and at x equals -3. So now we can go back. So now we fix our interval of convergence. Now it's going to equal, it's going to include -3. Well, let me write it. Yeah, it's going to include -3 and 3. So now the interval of convergence, note now it includes -3 and 3. Okay, any questions? Okay. Find our series expansion for equaling 1 over 1 plus 1 minus x squared. Okay. How would I do that? Oh my goodness. Okay. Let's go back to what we already know from before. There it is. Okay. All right, so we have the power series for 1 over x look like that. So what do you think I need to do to get the power series for 1 over x squared? Got 3 minutes. What do I need to do? This is one of the easiest part of the test. It is straightforward substitution. What do I need to do? Nobody has an idea? I know power series can be overwhelming. Okay, when I show you this, you're going to be like, oh my God, that was easy. Notice this is 1 over x, 1 over 1 minus x is equal to x to the n minus 1. So this is 1 over 1 minus x squared. So this is going to be equal to the sum n equals 1 to infinity. I'm going to have x squared to the n minus 1. So this is the sum n equals 1 to infinity of x to the 2 n minus 2. Any questions?
So I just want to make sure it's basically based on what x is, correct?
So here I had x, 1 over 1 minus x was the sum of x to the n minus 1. Here I have 1 over 1 minus x squared, so that's got to be the sum of x squared to the n minus 1.
So the negative, like, minus x or minus x squared, that doesn't matter, it's just based on what x is.
It just, right. So if I give you f of x equals 1 over 1 plus 3x. That would be, now this one converges. Again, the absolute value of x is less than 1. But remember, this is 1 over 1 minus r. So this is going to be the sum n equals 1 to infinity. A is 1 and r, so I get r to the n minus 1. So here r is going to be negative 3x to the n minus 1. Because r is negative, r here is negative 3. So that'll be negative 3x to the n minus 1. And this will converge when the absolute value of negative 3x is less than 1, or the absolute value of x is less than 1/3. Okay, that's it.